About it. So here we're doing exercise problem 5.11. We're told that we're operating a hydrogen fuel cell and it's operated at 75 degrees and at atmospheric pressure. So we can just say pressure is equals to 1 times 10 power 5 newtons per meter squared. And we have to find the Gibbs energy for, first of all, H2. Okay, so now we know that for Gibbs energy, we can use our formula that we derived in the exercise 5.8, I believe it was. And we have that dg, which of course is the change in Gibbs energy, is equals to what? Is equals to negative s dt plus v dp plus mu dn. Now, one important thing is that we are operating at a constant pressure, atmospheric pressure, so dP is equals to 0, and we're working with 1 mole of hydrogen, so we're going to have the dN is equals to 0 as well. So our dG is just equals to sdT. Okay, so we have to remember that our T0 is equals to 25 degrees, and we're operating at 75 degrees. So our dT is equals to 50 Celsius or Kelvin. It doesn't really matter. I'm just going to put everything to, yeah, Celsius over here. And then we can find the S for H2 is equals to 130.68 from the end book. So we can just plug it in and we get that negative 130.68 times 50. And our final, of course, this is joules over Kelvin. So our final unit of measurement will be joules. So we can just plug this in the calculator now, 130.68 times 50, and we get is equals to negative 6,534 joules. That's our dG. Now, we could have actually used, instead of using dG, we could have used simply G and calculated what our G was. But then it means that instead of calculating just G at 75 degrees, we also have to calculate G at 25 degrees, which is then assumed to be our 0. So if we just take dg, we can find our results more directly because we're kind of finding the difference, hypothesizing that our g0 is equals to 0. Okay. Now we have to do the same thing for O2. Yeah, okay. And then we get the dg, again, is equals to negative s dt. In our case, our s is equals to what for O2? Again, we have to look at the back of the book, and we find out that it's equals to 205.14 joules per Kelvin. Our change in temperature, or dT, is still 50 Kelvin. Okay, all right. And then we get negative 205.14 times 50. The final unit is joules, so we can plug in a calculator. 205.14 times 50 is equals to 10257 joules. Of course, negative again. Now we have to do the same thing for H2O, and we get the dG is equals to, then we are given our oh no, sorry, actually we already said that the G for a mole of H2O is negative 237, so I don't have to really find this. Is, oh no, okay, for a mole at 25 degrees, okay. So I'm gonna find the G, try to find the dG, because it doesn't matter anyway. Let's see if it works. We have for H2O, it's as I think that in our case, our H2O is liquid and not gaseous. So I'm gonna take the S for liquid, and S for liquid is equals to 69.91 joules per Kelvin. And again, our dt is equals to what? Is equals to 50 Kelvin. So again, we have negative 69.91 times 50. Everything will be measured in joules. So plug in the calculator, 69.91 times 50 is equals to 3495.5 joules. Okay. Now, one thing that you have to take into consideration is that in this time, G0 is not 0. It's actually equals, G0 is actually 125 degrees, is equals to negative 237 kilojoules. Oops, here we have negative. So our dG is actually equals to, again, would be the G final minus the G initial, or 0. So we have negative 3495.5 joules minus negative 237 kilojoules. Okay. Oh, sorry. Here, this is the dG. We already found dG. Okay, I'm gonna rewrite it better. So it would be something like G final is equal to G0 plus dG, right? This makes more sense. Yeah. Okay, so we would find that G final is equals to, well, our G0 is equal to negative 237 kilojoules, and now we have plus, it becomes minus because this is a minus over here. Oops, okay, so minus 3495.5 joules. So we have 337,000, negative 337,000 minus 3495.5. I'm gonna get something. Oops, okay. And we get 240,495.5 joules. Or just 240.5 kilojoules. Of course, with a negative in front. Now we have to find the maximum electrical work done by the cell for 1 mole of hydrogen fuel. So now we can just assume that all the work has to be done by the electrical work. So we can just say that the G will be our delta G, because we're changing Gibbs energy, will be equals to the work electrical. And so it's going to be equals to, here with use actually chemistry, we know that our reaction will be O2 plus 1 half O2 plus H2 is equals to H2O. Okay, so in order to find the dG, here we have to use the G of H2O minus 1 half G of O2 minus 1 half of the G of H2. Okay, so we can gather all together. The G of H2, we just said was equals to negative 240,000 I'm just going to 0.5 joules minus, oops, I don't know why I put a half here. Okay, 240,000 joules minus becomes plus because our G for O2 is negative, and to be exact is equals to 10.3 kilojoules, 10.3 kilojoules, and then we have minus, again, becomes positive. G of H2, which was equals to 6.5 thousand, or 6.5 kilojoules. So we can put them all together. We have 240.5 negative 240.5 plus 10.3 plus 6.5, and we get negative 223.7 kilojoules. This is our, oh, actually I forgot to put the 1 half in front of here. that was a pretty bad mistake. So 1/2 that which equals to 5.65. We get 228 point. I'm just gonna say 4. That's good enough. Okay, so this is our final work. And we can say that our maximum electrical work is 228.4. However, we also have to count the fact that actually it's not going to be done all by the electricity. It's not going to be all electrical work, so we're not too worried about that. And then we have to compare to ideal performance of the cell at 25 Celsius. Well, at 25 Celsius, then the only work we're going to do is going to be given by the G0 of H2O, because the other two G's we assume they were equals to 0. So our electrical work will be simply equals to the 237 kilojoules. Yep, it will be of course negative 237 kilojoules. And we can find the ratio between the two, or we can find actually the how much is smaller by. So we can say that we're gonna have 237 minus what we have here, 228. I'm gonna keep it easy. Divided by 228, we get 237 128 divided by 228. So it's equal to 0.04% smaller. It's not big, but we can see, for example, that the work required will be smaller. So, for example, when we find out that at a higher temperature, we need to get rid of more entropy. So we have to dispose of more heat into the environment, and therefore we have to do more work. That was it for exercise 5.11. A little long on the explanation, not the calculations done.